So this is for 7.1. Okay, I'm going to tell you about square roots. So for instance, 36. There's two square roots of 36, aren't there? Let me use a thicker marker. Okay, so this has two square roots. Both 6 and negative 6. So negative 6 comma 6. Now, do you know why that is the case? Because if you take negative 6 and you square it, you get 36. And furthermore, if you take 6 and you square it, you get 36. So in fact, 36 has two square roots. Okay, now how do we show square root mathematically? So if I were to say, for instance, the square root of 256, okay, do this in a calculator. The square root of 256 is 16. And the reason for that is because when you take 16 and you square it, you get 256, don't you? If I specifically want the negative square root, when we use this symbol, you see this symbol that I'm tracing out? This flat line across the top is called the vinculum, and then this portion in the front is called the square root symbol. Sometimes we refer to the whole thing as the square root symbol. When we use that symbol, we mean the positive square root. If I specifically want to ask for the negative square root, I'd put a negative sign in front of it. So negative square root of 256. In that case, I would say negative 16. All right, how does that look? We can also use fractional exponents if we want. So another way of saying this, is 256 to the 1/2 power is equal to 16. Square root means 1/2 power. Okay, so how does that look? Well, how about something like, for instance, the square root of 255? 255. I just found the square root of 256, didn't I? Well, that was 16. It comes out clean. But in this case, 255, the best I can do is an approximation. So that wavy equal sign means approximately. If you do this in a calculator, it's 15.969. Make sure you look at the owner's manual for whatever calculator you're using so that you know how to find the square root. So 255 is not a perfect square. Now, I know that I'm repeating myself here, but the square root of 256, you remember, was 16. So you notice that 256, when I take the square root of that, it comes out exactly. When I take the square root of 255, it's some really long decimal. So we say that 256, that's called the radicand. The thing beneath the vinculum is called the radicand. The radicand here is a perfect square because its square root is a whole number. Well, 255 is not a perfect square because when I take the square root of 255, I wind up with some messy decimal. You see that? Okay, now let me complicate this. What if I have, for instance, the square root of negative 9 squared? Okay, well, first work on the radicand. If you take the negative 9 and you square it, you get 81, don't you? So this becomes the square root of 81, which turns out to be positive 9. All right, how does that look? You okay with that? Okay, what if I have variables involved? So for instance, the square root of 144 x to the 6th power. Okay, I can split this up into the square root of 144 times the square root of x to the 6th. See, I can split that up. Now remember that square root means 1/2 power. So the square root of 144, I could write that as 144 to the 1/2 power. I don't really need to because my calculator can tell me that that's going to be 12. But for the x to the 6th power, I do want to write that with a 1/2 exponent. Do you see this? Okay, well, the square root of 144 is 12, isn't it? Okay, now what about this part? Okay, so take a look at this here. Let me circle it. X to the 6th to the 1/2 power. You see that thing I'm circling there? Remember that rule of exponents that says that when you're raising a power to a power, you multiply the exponents? Remember that? Okay, so I can actually rewrite that as x raised to the power of 6 times 1/2. You see, I multiply the exponents. When you raise a power to a power, you multiply the exponents. So tell me, what is 6 times 1/2? What? That's 3, isn't it? So this turns out to be 12x cubed. And that, my friends, is the answer that he's looking for in this particular case. Okay, how does that look? Okay, so square root is something that you probably learned about in Math 45 or elementary algebra, or whatever you took preceding this class. But now I want to tell you about cube root. Cube root or cube roots, plural. I know I write kind of sloppy, but I'm like a medical doctor. Have you ever seen the writing of a medical doctor? He's always really sloppy. So I'm kind of like a medical doctor. I write sloppy. Okay, so consider this. If 8 cubed is equal to 512, what if I want to go backwards? I'd say the cube root of 512. Now to indicate that it's a cube root and not a square root, I'd put a little 3 in there. That 3 is called the index. That's called the index. If no index is shown, that means it's a square root. But if I put some other number there, that means it's some other root. In this case, it's the cube root. So I say the cube root of 512 is 8. You see that? If I want to write this using exponents, I could also say 512 to the 1/3 power is equal to 8. So that's saying the same thing. Got that? So for example, let's throw some algebraic expressions into this. Let's just say I want the cube root of, I'll say x to the 51 power. Okay, well, it's really convenient here to write this using exponents. So this will be x to the 51 power raised to the 1/3 power. Now, there is a rule of exponents. It says that when you raise a power to a power, that simply means you multiply the exponents. So you see what I'm doing there? Okay, so what is 51 times 1/3? What is that, 17? So this, my friends, turns out to be x to the 17th power. How does that look to you? Okay, now I'm going to tell you about just general nth roots. Okay, so now I'll say nth roots, where the index isn't necessarily 3. Okay, so I'll show by example. So for instance, let's just say I've got the 7th root of x to the 21 power. Okay, well, following the pattern that I've been following before, the index, 7, will actually become the denominator of the fractional exponent. The numerator in this case will be 1. Okay, so I'm going to write this as x raised to the power of 21 times 1/7. Okay, let me throw in this step. 21 times 1/7, isn't that the same thing as 21 over 7? So a kind of a shortcut way to do this would be to take the exponent on the base, x, and make that into the numerator of the fractional exponent. The index becomes the denominator. Okay, so notice that the exponent, 21, the exponent becomes the numerator, the index becomes the denominator. Okay, so what this becomes is x to the 3rd power. How does that look? Okay, try this. For instance, the 5th root of negative 32, I'll say x to the 15th, y to the 10th. Okay, split this up into 3 parts. The number part, the 5th root of negative 32, and you could have a calculator that does this, finds 5th roots of a number. The 5th root of x to the 15th, the 5th root of y to the 10th. Okay, so this will be, your calculator might have a button that'll allow you to find the 5th root of negative 32. Check your owner's manual. So that'll be negative 32 to the 1/5 power, x to the 15th to the 1/5 power, y to the 10th to the 1/5 power. Okay, so negative 32 to the 1/5. You know what that is? Negative 2. Okay, second one. X raised to the power of 15 times 1/5. 15 times 1/5, what is that? What 15 times 1/5? I'm multiplying these two. 15 times 1/5, isn't that 3? How does that look? Okay, and then the next one, what do I have here? Y. So y raised to what power? Okay, so raised to the power of 10 times 1/5. What's 10 times 1/5? Is that 2? So x raised to the third power, y raised to the second power. So this right here is the answer he wants. Negative 2x cubed y squared. How does that look? Okay, now be careful here, because if the index is odd, then it doesn't matter what the radicand is. But if the index is even, then you have to have a positive radicand. Okay, did you catch that? Okay, so if you're taking the root of something, the nth root of something, so the nth root of x, I'll say. Okay, if n is odd, then x can be anything. On the other hand, if n is even, then I need for x to be greater than or equal to 0. Because if x is less than 0, then I'm going to wind up with an answer that's not real, and that's beyond the scope of this class. Okay, so for instance, consider this. I want the fourth root of negative 16. Okay, so what can you tell me about the radicand? The radicand is negative. Uh-oh. And the index is even. Okay, if the index is even and the radicand is negative, then I'm in trouble. So this is not real. That is not real. You may have learned about this in Math 45. What is I? I refers to the square root of negative 1. I is what we call the imaginary unit. So what that means for this, the fourth root of negative 16, there are actually 4 answers to this. Okay, so the 4 answers are positive or negative square root of 2 times 1 plus I. Okay, those are 2 of the answers. The other 2 answers, positive or negative square root of 2 times 1 minus I. Those are actually the 4 answers, but obtaining those answers is a bit beyond the scope of this course, so just take that on faith. But these are the 4 answers. But the point of this class is that if you've got an even index, then x has to be greater than or equal to 0 for us to have real answers. Okay, what about this? Simplify. Simplify a square root of x squared over 16. I'm going to say y squared. Split this up into the square root of the numerator over the square root of the denominator. Okay, so that numerator, that's like saying x squared to the 1/2 power. The denominator, I can actually split that up into the square root of 16, or 16 to the 1/2 power, I don't care, times y squared to the 1/2 power. So the numerator is obviously going to become x, right? The denominator, the square root of 16 is 4. Y squared to the 1/2, that's y, isn't it? So we have here x over 4y. Okay, how does that look? X over 4y? Okay, lastly, remember function notation? Function notation. Let's just say that f of x is equal to the square root of, let me say, 4x plus 7. Okay, how does that look? Okay, I want to find f of 3. F of 3, that just means I'm replacing x with 3. Okay, so I'm going to have here 4 times 3 plus 7. Simplify under the vinculum. So 4 times 3, I think that's 12. 12 plus 7. Okay, so that will be the square root of 19. And that's the exact answer. He might ask for a decimal approximation. So how does that look? Okay, consider this. What is the domain? So I have here g of x is equal to the cube root of x plus 4. So can you tell me what the domain of this is? Okay, now remember I said that if the index is odd, then it really doesn't matter what the radicand is. We only have to be careful where the index is even. So in this case, due to the fact that that index is odd, the domain of this The domain of this is unrestricted, so I would say the interval from negative infinity to positive infinity. How does that look? Okay, now what if I want to graph this? Okay, so graph the cube root of x plus 4. Okay, I'm going to move this over a little bit. Actually, maybe if I zoom out. Okay, so I'm going to set up a table of x versus y, because I want to graph this thing. Okay, so what am I going to use for my x values? Okay, well, I'll be a little creative here. Let me put in here, I will say negative 4. Put it down here, though. Negative 4. So if you stick negative 4 into this, you'll have negative 4 plus 4, which is 0. The cube root of 0 is still 0, so I'll have the point negative 4, 0, won't I? Okay, now let me stick in, for example, negative 5. So if x is negative 5, put negative 5 in there. Negative 5 plus 4 is negative 1. What's the cube root of negative 1? Still negative 1? Okay, so this will be negative 1. Do you know how I'm doing this? Okay, what if I stick in negative 12? Okay, so I'm getting lazy here. Let me show you how I'm actually doing this. So, for instance, g of negative 12. Okay, and this is how I was doing it for the others also. This will be the cube root. X is being replaced with negative 12, so negative 12 plus 4, right? Okay, so what's negative 12 plus 4? What? That's negative 8, isn't it? Okay, got a calculator? What's the cube root of negative 8? That's negative 2, isn't it? So negative 12, negative 2. See that? Okay, now let's just say that I have, for instance, okay, what have I used? Negative 12, negative 5, negative 4. What if I use negative 3? Put negative 3 in here. Negative 3 plus 4 is 1. The cube root of 1 is still 1. Okay, what if I stick in maybe one more value here? What if I stick in positive 4? If I stick in positive 4, 4 plus 4 is 8. The cube root of 8 is 2. Well, what if I stick in 5? Well, if I stick in 5, 5 plus 4 is 9. Okay, let me show it down here. Okay, g of, what did I say, 5? So that's the cube root of 5 plus 4. That's the cube root of 9, isn't it? Okay, that's not going to come out nice, is it? What's the cube root of 9? Got a calculator? Okay, so let me use my own calculator off to the side here. You can't see it. Okay, so that will be 2.08 approximately. So it doesn't come out clean. That's going to be a hard number to work with. So 2.08. Okay, so make sure you look at the owner's manual of your own calculator so you know how to find the cube root. Okay, so how many points do I have? 1, 2, 3, 4, 5, 6. 6 points. So let me graph this thing then. Okay, so here's some graph paper I threw together really fast. See the graph paper here? What? Okay, so what are the points that I've got? Negative 12, negative 2, so where's that? Negative 12, negative 2. Okay, so negative 12, negative 2 would be there. And then the next point, negative 5, negative 1. 1, 2, 3, 4, 5. Negative 1 is right there. Next point, negative 4, 0. 1, 2, 3, 4, 0, right there. Next point, negative 3, 1. So a 1, 2, 3, 1 is right there. Next point, 4, 2. Okay, so where is that? 1, 2, 3, 4, and then 2 is right here. And then the next point, 5, 2.08. So a 1, 2, 3, 4, 5, and then 2.08. Well, it'll be somewhere approximately there. Okay, so then I'm going to connect the dots. Be better if I had a French curve to do this, but I'll eyeball it as best I can. So it's going to look something approximately like this. Okay, so when I graph that function, take a look at it. When I graph that function, it'll look something like this. So there you have it.